that is attached, or depending on the group that is attached at nitrogen 1. I think, I hope that is that the different sulfonamides will have different pKa's, and this is explained by the substituent. Of course, the substituent, and the substitution on the substituent, whereby we are saying you can have alkoxy groups, you can have alkyl groups, and both alkoxy groups and alkyl groups will decrease the electronegativity of the respective heteroatoms because they are pushing electrons into the system, and therefore the withdrawing ability of the heterocyclic ring will be reduced when you have groups that are substituted on that ring, and those groups are electron donors. Again, we are still looking at crystallurean, and all we are saying is that those sulfonamides, those sulfonamides keep confusing. Those sulfonamides, and okay, they are also called sulfonamides actually. Those sulfonamides or sulfonamides acetal derivatives are sparingly soluble in water and excreted almost in urine. So we can say for those sulfonamides, for the sulfonamides and the acetal derivatives, which are sparingly soluble in water and excreted or treated in urine, there will be precipitation in the kidney, bringing about crystalluria. So this is just a summary of what we are saying, that when you have sulfonamides or sulfonamides, remember we did call them sulfonamide derivatives, sulfonamides which are sparingly soluble in water or sparingly soluble, then when they get into the kidneys, because of their low ionization, they will be precipitated, and indeed they will precipitate crystalluria. And crystalluria is just you getting this drug, the drug itself being precipitated in the kidneys, and you can imagine how sensitive the kidney is. So if you get crystals of the drug, those crystals will damage. The crystals of that drug will totally damage the urine, the kidney. They will damage the tubules of the kidney, and therefore you must try the best you can to avoid that from happening. And this is what we were saying. This is the Henderson-Henselberg's equation. This is the Henderson-Henselberg equation, where we are saying the pKa of a drug equals, that is the pKa we are looking at. If we are looking at sulfoxazole, or we are looking at whichever drug we are looking at, will equals to the pH of the urine plus the log of the ionized form of the drug divided by the ionized form of the drug. This is the buffer. This is the equation for buffers. This is the equation for buffers, and we are only saying for this drug, it has a certain pKa, and that pKa will equal to the pH of urine plus the log of our ionized form of the drug divided by ionized form of the drug. And what we were saying, if you have 50% ionization, it will be the concentration of an ionized drug and the concentration of ionized drug will be equal. So the whole of this, an ionized drug over ionized drug, will equal to 1. And we know the logarithm to base 10 of 1 is 0. I believe you can remember that. You've done mathematics and you did logarithms. So the logarithm in base 10 of an ion, if the concentration of ionized drug is equals to the concentration of an ionized drug. In other words, if the drug is 50% ionized, the ionized concentration will equal to ionized concentration. Therefore, ionized concentration divided by ionized concentration will equal to 1, because if you have 50 and 50, 1. The logarithm of 1 is 0. And that is where I was deriving the equation that at 50% ionization, the pKa of the drug will equal to the pH of the urine. So at 50% ionization of the drug, the pKa of the drug will equal to the pH of the urine. And that is the principle we were using, that you are trying to decrease. The pH of the urine is around 6. So if you want this drug to be 50%, at least merely just 50% ionized, you'd want the pKa of the drug to approach the pH of the urine. So the pKa of the drug should be coming lower, down, down, down. When it gets to 6, you 50% ionization, and of course the lower it is, like we have said in surface oxides, the way it is 5, then you even have more than 50% ionized, because when the pKa of the drug goes much lower, it means the ionized concentration is much higher than the unionized concentration. For this pKa to go much lower, it means you are adding this number here, you are adding is much smaller. So the concentration of the ionized drug will be much higher, and the concentration of the ionized drug will be much lower, and therefore there will be, when the pKa is much bigger than the pH, the pKa is much smaller than the pH, then the concentration of ionized drug will be much higher, and that is indeed what you want. So this is just a simple analogy just from looking at this, and you're saying if pH of urine is equal to pKa of drug, ionized is divided by unionized equals to 1. If pKa of drug is greater than pH of urine, ionized divided by ionized is greater than 1, therefore decreased solubility, because you can see unionized over ionized is greater than 1, so the unionized drug is more. If pKa of drug is less than pH of the urine, unionized, as we have said, divided by ionized is less than 1, and therefore increased solubility. pH of urine is about 6, and pKa of sulphonamide, the prototype, is 10.4. So you can see the solubility of sulphonamide will be very low because of that big difference in pH and pKa. The drug present in an ionized form is very low. It's very low solubility, and therefore crystalluria. So this is a very important equation. This is the Henderson-Hensselberg's equation. Henderson-Hensselberg's equation. You must have done it when you're looking at buffers, and it is able to help us understand why decreasing the pKa of the sulphonamide will result in an increased solubility of the drug in the lower pH. So you must get those terminology. So you are decreasing pKa of the drug. Decreased pKa of the drug will increase the solubility of that drug in the slightly highly acidic, or in the urine, which has slightly lower pH. And of course, when you do, once you decrease the pKa of the drug, the urine is acidic, then you will increase the concentration of, even according to the Henderson-Hensselberg's equation. And as we have said, that is why we structurally modify sulphonamide to give to place in place of the 1 hydrogen atoms, we place an electron withdrawing group, and the stronger the electron withdrawing group, the higher the acidity, or the lower the pH of the drug, and the lower the pKa of the drug. And once the drug has a low pKa in the urine, it will be well ionized, and you do not have to do alkalinization. The drug will be well ionized even in the acidic pH, and therefore you will avoid crystalluria. For the other drugs which have low ionization, then you must do what it takes. Either you do alkalinization, as we have said, you do alkalinization, or you must also advise to take a lot of water if you are going to prevent the crystalluria from. This we have already mentioned. It's for some of those drugs that will be acetylated, and acetylated amide is, of course, even having much lower water solubility than even the drug itself, and therefore you require to do a structural modification so that the drug can have solubility. So to solve problem of crystalluria, you've already said drinking large amount of water or increasing the urine flow. But therefore, we did mention, increase the urine flow, you will not allow for the seeding process to occur. So drinking large amounts of water, increased urine flow by increasing rate of glomerular filtration, you do not allow the seeding or the crystallization of the sulphonamide to occur. Also, number 2, you can do combination therapy. When you do combination therapy, remember, there is what we call the triple therapy, where you put 3 sulfonamides together. When you put the 3 sulfonamides together, it means the concentration of each of the sulfonamides will be much, much lower within the triple combination. So you're putting 3 sulfonamides, and the concentration of each of the sulfonamides will be lower in the combination. So therefore, you will not be able to overshoot its solubility. You will not overshoot its solubility product, and therefore that drug will remain safe. And sometimes you do mix 3 sulfonamides. So the 3 sulfur drugs at times are mixed is sulfadiazine, sulfamerazine, and sulfamethazine. So you mix sulfadiazine, sulfamerazine, and sulfamethazine. Only 1/3 of the amount of each drug is used, giving the same bacterial action, but each one is present in amount less than its solubility product. Therefore, no precipitation. What is my throat? Cords are giving up very easily. So again, please do understand the concept there. You're bringing in 3 sulfonamides, sulfadiazine, sulfamerazine, sulfamethazine. The only difference between sulfamerazine and sulfamethazine, they have the pyrimidine ring. All of them have the diazine ring, but one has one methyl group, whereas the other one has 2 methyl groups. So you are mixing these 3 sulfonamides, and because you are mixing the 3 combination therapy, the dose of each of them within the combination is lower than expected. It's a third, as we have said, to be a third, and therefore you will not be above the solubility product of that drug, and therefore it will not be above the concentration of that drug in solution will not be above its solubility product, so it will be able to remain in solution and not be precipitated. All the sulfonamides have the same side effects, so even if you put the combination therapy of 3, you're not exposing the person to just sulfonamides. So we cannot say that there will be increased toxicity because these are 3 sulfonamides. Indeed, we are having an advantage that because of the fact that we are decreasing the dose of each of the sulfonamides, and therefore not going above their solubility product, we are having an advantage of eliminating the crystal urea. We also did mention increase the pH of urine through alkalinization because weak acids are more soluble in basic media. Decrease the pKa of the drug, which we have discussed a lot, by N1 substitution with electron withdrawing group. For example, of course, these R here, this R, in that R, you put an electron withdrawing click ring. The more powerful it is, the higher the solubility of the sulfonamide. This is just what we have just said. Combination of sulfur is more water soluble than a single drug at the same total concentration. This is the basis of triple sulfonamide mixtures using clinically, and the bacterial effect is additive. As use of triple sulfurs allows increased efficacy without increasing risk of adverse effects. So we are only saying this is what we had said, that the antibacterial activity is additive. You add for sulfadiazine, sulfamethazine, and the other one sulfamerazine. So the effect is additive. After all of them are sulfonamides, but none of them is able to be beyond its solubility product, and therefore you have that addition, that advantage that we have already said. This we have already mentioned, because we're going to mention other combinations, because we do have other combinations. Those ones I want to mention them at their own time. What is here? So yeah, so here we have, in case there's any sulfonamides we had not mentioned. Let's see whether there's any. So I was saying you have sulfur. One is which one? So there is sulfonilamide, amino group. This is sulfadiazine. This is sulfadiazine. and sulfadiazine has that nitrogen, and then we have sulfamethazine, and you can see the sulfamethazine is just sulfadiazine, but of course ortho meta. So sorry, ortho meta, but sulfamethazine has 2 meta methyl groups. Remember, we did mention when you have the meta alkyl groups, there is increased binding, and there is of course also increased. There's also increased. There's increased binding, and there is also increased protein binding, and that would result in longer duration of activity. When you compare that with, and of course, because of those 2 methyl groups, you can't see the pKa of that drug is 7.4 compared to sulfamerazine. Sulfamerazine still having the diazine ring, but with only 1 meta, only one meta methyl group. And because you say the methyl groups are electron donors, when you have only 1 electron donor, then that will influence the electron withdrawing effect of the nitrogen to a lesser extent than when you have 2. So you can see the sulfamethazine, that is the sulfamethazine, sulfamerazine. That's the only difference. Sulfamethazine has 2, sulfamerazine has 1, sulfadiazine has none. So you are mixing sulfadiazine and of course sulfadiazine, you can be able to see its pKa will be also much lower than the pKa of sulfamerazine. I have explained again. Then you have, of course, sulfamethoxazole. People have a lot of mistakes here. Another mistake here. No, sulfamethoxazole, not sulfamethoxazole. Yeah, sulfamethoxazole, not sulfathiazole. So sulfamethoxazole, and you can see with sulfamethoxazole, it has now a nitrogen and an oxygen. In place of 1 nitrogen, we have put an oxygen. An oxygen is a more powerful electron withdrawer, and no wonder it has a slightly lower pKa than our sulfadiazine. Then you see the one I was telling you, in the other one there was a mistake. This is now the correct structure of sulfoxazole. It's the correct structure now of sulfoxazole, where the oxygen, that's the only difference. There's a reversal if you look at this. So just a reversal, that the oxygen is the one which is attached to the carbon, which is attached to the nitrogen. And because oxygen, as I've said, is a more powerful, it's more powerful than nitrogen, more powerful than sulfur. Sulfur is the weakest, followed by nitrogen, and oxygen having the highest electron withdrawing power. So now, because oxygen is more powerful as an electron, is closely attached to it's the one which is attached, the carbon which is attached to the nitrogen, then that's why we are saying sulfoxazole has a pKa of 5 compared to sulfamethoxazole, which has a pKa of 6.1, sulfadiazine 6.5. And that's what I was saying. One should be able to, looking at these structures, you should be able to tell which of them has a lower pKa than the other, just by understanding which of the groups is a more stronger withdrawer than the other. This we have already mentioned, where you have sulfathiazole and sulfadiazine. The replacement of thiazole ring with the diazine ring makes the diazine ring, the sulfadiazole more water soluble, less crystalluria, and even its acetylated metabolite still remains water soluble and therefore lesser toxicity. I think these are just examples. You can try to give as many examples as possible. So these are still examples of what we are looking at: sulfamethoxazole, sulfamerazine, sulfamethiazole, sulfamoxazole. So I think we will let us try to learn the ones which are very common: sulfamethoxazole, sulfamerazine, sulfur. That one is not very common. Sulfamethazine, we have mentioned. Sulfoxazole, we have mentioned severally. Sulfapyridine, and for sure this is not, these people do bad structure. This is for sure is not sulfapyridine. No. sulfopyridine will have this as a pyridine ring. Indeed, this is sulfothiazole. So unfortunately, I didn't draw my own structures. I got them from the books and or the other sources. But at least make sure you can draw some of these structures. Be able to draw the structure of sulfamethoxazole. Be able to draw the structure of sulfamerazine, sulfamethazine. You see, remember you measured. They say there is sulfamerazine, sulfamethazine, sulfamethoxazole, sulfamethoxazole, sulfamethazine, sulfisoxazole, sulfapyridine. Those are some of the very common. At the end of it, I will give you the very common sulfonamides that for which structure you should be able to at least have an idea. You can see even in the books, if you're not careful, you can get them wrong. Some of them, they are drawing them wrongly. But I think there is one where we had them a bit better. So we have said the more common ones, sulfanilamide definitely is a prototype, sulfothiazole, important, sulfisoxazole, also important. And I say this is not the structure of sulfisoxazole, kind of is on that side, sulfadiazine. So the ones I have here are the sulfonamides. I would expect you to know. So sulfanilamide, sulfothiazole, sulfisoxazole, sulfadiazine, sulfamethiazine, and of course there was sulfamerazine. Methazine has two, merazine has one. Sulfacetamide, sulfadoxine. This is as I said earlier, this one is a long acting. It was being used in the management of malaria when there was not so much distance. Sulfamethoxazole, a very, very, very important sulfonamide, because this is combined with trimethoprim to give us septrin. So this is combined with trimethoprim, very, very important. And then, of course, as I said, you see the ones they are drawn could not have been sulfopyridine. Sulfopyridine must have the pyridine. So note some of this: sulfanilamide, sulfothiazole, sulfisoxazole, sulfadiazine, sulfamerazine, sulfacetamide, sulfadoxine, sulfamethoxazole, sulfopyridine. Those are some of the important sulfonamides. They're not very difficult to remember because their names are also derived from their structure. So now from there, I want us now to look at, we have looked at one type of combination therapy, but that is what we call the triple sulfurs. Triple sulfurs, where you are taking just sulfonamides, different ones, sulfadiazine, sulfamerazine, sulfamethazine, and you're putting them together where you know that in that combination, each of the sulfonamides will be the 1/3 of the expected if you gave it alone. And therefore, you, of course, know that since the dose of each individual sulfonamide is much lower than if you gave it alone, none of those sulfonamides will be above their solubility product, and therefore they will maintain good solubility. But there is another type of combination therapy whereby you combine two drugs or combine two compounds. These two compounds are acting on the same pathway. There's another combination therapy of where you have sulfonamide plus another compound. You take these two compounds, one of them is a sulfonamide, you combine with another compound which is not a sulfonamide, but they are acting on the same pathway of folic acid, synthesis or dihydrofolate acid synthesis. And because they are acting on the same pathway, but they are different in structure, we call it sequential blockade. You're talking about sequential blockade, where you are blocking the pathway for the synthesis of the dihydrofolic acid at different positions. Therefore, you are using two different molecules or two different molecules to inhibit the different enzymes. Remember, dihydrofolic acid synthesis, and then we talked about dihydrofolate reductase. So you are using two different molecules with different structures to block two different enzymes, which all responsible for synthesis of the same molecule. So you're doing sequential blockade. You start with the first one, you block it fast. So you block the first one. But you see, because it's competitive inhibition, the microorganism might have acquired resistance various stages. So you hit it again. So if the first time, because of competitive inhibition, it still is able to make a bit of the dihydrofolic acid, you hit it again. It's supposed to reduce the dihydrofolic acid to tetrahydrofolic acid. You hit that enzyme again at the same pathway. That is what we call sequential blockade. So remember, we did talk about para-aminobenzoic acid. It must be incorporated in the synthesis or in the ultimate synthesis for you to have the ultimate synthesis of the folic acid or the dihydrofolic acid. So the PABA is taken up by the enzyme dihydropteroate or dihydrofolate synthetase. You can either call it dihydropteroate or dihydrofolate synthetase. And this is where you put in your sulfonamide. Remember, the sulfonamide has structural resemblance with the para-aminobenzoic acid. So it is taken up in a competitive inhibition by the hydrofolate synthetase enzyme, and it immediately blocks that enzyme. But do remember, you do have some microorganisms that have acquired resistance. Either they are producing a lot of para-aminobenzoic acid, or they are distorted in their shape and therefore cannot bind. All will bind the sulfonamide, but they will still be able to bind the para-aminobenzoic acid. So there are some microorganisms that have acquired resistance, and those that have acquired resistance will still pick up the para-aminobenzoic acid in the presence of sulfonamide. So they will still go, again, this step is still the dihydrofolate synthetase. They will still be able to form the dihydrofolic acid, even in the presence of the sulfonamide, because of resistance. So now you bring in another molecule, like what we call trimethoprim. Trimethoprim, we use it for bacterial infections. And you can see now the trimethoprim is not acting on dihydropteroate synthetase. It is inhibiting the second enzyme within that pathway of synthesis of tetrahydrofolic acid. It is inhibiting the dihydrofolate reductase. This dihydrofolate reductase enzyme is found also in the host. So this enzyme is found in the host, and that is why we are hesitant, especially when you talk about when in pregnancy. In pregnancy, you are hesitant to give some of these drugs, because you remember the dihydrofolate synthetase reductase, the dihydrofolate reductase will be required in the host to reduce your folic acid to tetrahydrofolic acid, even in the host, because what the molecule which is used as a cofactor is the tetrahydrofolic acid, not the dihydrofolic acid and not the folic acid. So this enzyme, very important both in the host and also in the microorganism to further reduce the dihydrofolic acid to the tetrahydrofolic acid. And therefore, you use trimethoprim. So you make a drug which is a combination of a sulfonamide and trimethoprim. And you can see trimethoprim has a different structure. So this is the structure of trimethoprim. You can see that structure is different. Nothing similar with the sulfonamide. So you can see it has this 1, 2, 3, those 3 methoxy group, and of course joined to this aminopyrimidine derivative. So this is our trimethoprim. So you put it in combination in the right amount and you make it into one tablet, trimethoprim plus sulfamethoxazole, and it makes you a water drug. And that water drug, it is because it has sequential blockade. It has sequential blockade of the microorganism, and therefore gives you much better activity. Yet being reminded that decrease in tetrahydrofolate acid synthetase, you decrease purine and pyrimidine bases synthesis, decreased DNA synthesis, and they stop growth of the bacteria. And that's why you also have to be careful here in case you have in pregnancy that you do not give some of these products, because you will have decrease in pyrimidine basis. The young one that is growing requires a lot of these purine basis because of the development, and therefore these drugs are contraindicated in pregnancy.